Section 230.42a of the National Electrical Code addresses the minimum size and rating of service entrance conductors. It dictates that the ampacity of the service entrance conductors before the application of any adjustment or correction factors must not be less than the non-continuous loads plus 125% of the continuous loads. It is crucial to differentiate between continuous and non-continuous loads when applying this section of the code. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Examples of continuous loads include but are not limited to lighting in commercial buildings, HVAC equipment, and certain types of industrial machinery. Non-continuous loads are those where the maximum current is not expected to continue for 3 hours or more. Common examples include general use receptacles, small appliances, and most residential lighting. In a residential setting, the typical electrical loads do not meet the definition of continuous loads. Appliances such as refrigerators, ovens, and washing machines cycle on and off, and lighting is rarely used continuously for 3 hours or more. Therefore, applying the 125% factor to the entire calculated load for a residential dwelling is generally not required or appropriate. The standard method for calculating the service load for a dwelling unit involves using the procedures outlined in Article 220 of the National Electrical Code. Article 220 provides detailed guidance on calculating general lighting loads, small appliance branch circuit loads, laundry branch circuit loads, and the loads for individual appliances. The general lighting load is calculated based on the square footage of the dwelling unit. Table 220.12 specifies the unit load per square foot, which is typically 3 volt-amps per square foot for dwelling units. Small appliance branch circuits are required to be calculated at 1500 volt-amps each. Section 220.11 specifies that a minimum of 2 small appliance branch circuits must be included for the kitchen and dining areas. Laundry branch circuits are also calculated at 1500 volt-amps. Section 220.11 requires at least 1 laundry branch circuit to be included. The loads for individual appliances such as ranges, ovens, and air conditioners are calculated based on their nameplate ratings. Article 220 provides specific rules for calculating these loads, including demand factors that can be applied to account for the fact that not all appliances will be operating at their maximum load simultaneously. After calculating all the individual loads, demand factors are applied according to the tables in Article 220. These demand factors reduce the overall calculated load to account for the diversity of loads in a dwelling unit. For example, Table 220.42 allows a demand factor of 75% to be applied to the first 3 kVA of lighting and receptacle loads, and 35% to the remainder of these loads. Once all the demand factors have been applied, the total calculated load is used to determine the minimum size of the service entrance conductors and the service disconnect. Section 230.42b provides guidance on sizing service entrance conductors for dwelling units. It states that the service entrance conductors must have an ampacity equal to or greater than the calculated load. The calculated load is determined using the procedures outlined in Article 220. In the specific scenario of a 728 square foot condominium unit, a calculated load of 144 amps indicates the total demand expected from the unit's electrical system under normal operating conditions. This calculation would have taken into account factors such as general lighting, small appliance circuits, laundry circuits, and any fixed appliances like air conditioners or electric heaters, as per Article 220. Given this calculated load of 144 amps, a 150 amp service would indeed be sufficient. This is because the 150 amp service provides a capacity that meets or exceeds the calculated demand, ensuring that the electrical system can handle the anticipated load without overloading. The engineer's suggestion to increase the load by 125%, resulting in a requirement for a 200 amp service, is not appropriate in this context because residential loads, as discussed earlier, are not typically classified as continuous loads. Applying the 125% factor is generally reserved for situations where loads are known to operate continuously for 3 hours or more, which is not the case in a typical residential setting. It is important to understand the distinction between continuous and non-continuous loads and to apply the appropriate sections of the National Electrical Code when calculating service loads. Applying the 125% factor to non-continuous loads can result in oversizing the service entrance conductors and the service disconnect, which can increase the cost of the electrical installation without providing any additional benefit. In summary, the engineer's interpretation of the code is incorrect, and a 150 amp service is sufficient for the 728 square foot condominium unit with a calculated load of 144 amps. The 125% factor in section 230.42a is not applicable to residential loads, which are typically non-continuous. It is essential to accurately calculate the load using Article 220 and to select a service size that meets or exceeds the calculated demand. Furthermore, it is essential to consider any future expansion or potential changes in electrical usage when determining the appropriate service size. While a 150 amp service may be sufficient for the current load, it is prudent to evaluate whether the electrical needs of the dwelling unit are likely to increase in the future. For example, if the homeowner plans to install additional appliances or equipment, such as an electric vehicle charger, the service size may need to be increased to accommodate the additional load. In addition to considering future expansion, it is also important to comply with any local codes or regulations that may require a larger service size. Some jurisdictions may have specific requirements for the minimum service size in dwelling units, regardless of the calculated load. Therefore, it is always advisable to consult with the local building department or a qualified electrical inspector to ensure that the electrical installation complies with all applicable codes and regulations. The National Electrical Code is a comprehensive set of standards for electrical installations, and it is essential to have a thorough understanding of its requirements to ensure a safe and reliable electrical system. The code is updated every 3 years to reflect changes in technology and industry best practices. Therefore, it is important to stay current with the latest edition of the code and to seek guidance from qualified professionals when necessary. Moreover, factors such as voltage drop and available fault current should also be considered when designing an electrical service. Voltage drop occurs when the voltage at the point of utilization is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code specifies the maximum allowable voltage drop for branch circuits and feeders. Available fault current is the amount of current that would flow in a circuit under fault conditions, such as a short circuit. It is important to select electrical equipment with an interrupting rating sufficient to handle the available fault current to prevent equipment damage or personal injury. Fault current calculations are typically performed by a qualified electrical engineer. Furthermore, it is important to ensure that all electrical work is performed by qualified and licensed electricians. Electrical work can be dangerous if not performed properly, and it is essential to follow all safety precautions to prevent electrical shock, fire, and other hazards. Licensed electricians have the training and experience necessary to perform electrical work safely and in accordance with the National Electrical Code. It is also advisable to have the electrical installation inspected by a qualified electrical inspector to ensure that it complies with all applicable codes and regulations. Electrical inspections can help identify potential safety hazards and ensure that the electrical system is installed correctly. In addition to the National Electrical Code, there may be other applicable standards or guidelines that should be considered when designing and installing an electrical system. For example, the National Fire Protection Association develops standards for fire protection and life safety, and these standards may contain requirements related to electrical installations. It is also important to consider any manufacturer's instructions or recommendations for electrical equipment. Following these instructions can help ensure that the equipment is installed correctly and operates safely and efficiently. Another important aspect of electrical system design is coordination. Coordination involves selecting and coordinating the ratings of overcurrent protective devices, such as circuit breakers and fuses, to ensure that a fault or overload on one circuit does not cause a disruption of power to other circuits. Proper coordination can help prevent nuisance tripping and minimize the impact of electrical faults. Coordination studies are typically performed by a qualified electrical engineer. Furthermore, it is important to consider the environmental conditions in which the electrical equipment will be installed. Electrical equipment may need to be rated for use in wet, damp, or corrosive environments. The National Electrical Code specifies the types of enclosures and equipment that are suitable for use in different environments. It is also important to protect electrical equipment from physical damage. Equipment should be installed in a location where it is not likely to be damaged by impact, vibration, or other physical hazards. Protective barriers or enclosures may be necessary to prevent damage. In addition to the technical aspects of electrical system design, it is also important to consider the aesthetic aspects. Electrical equipment should be installed in a way that is visually appealing and does not detract from the overall appearance of the building. Conduit and wiring should be concealed whenever possible, and equipment should be neatly arranged and labeled. It is also important to consider the accessibility of electrical equipment for maintenance and repairs. Equipment should be installed in a location where it can be easily accessed by qualified personnel. Sufficient workspace should be provided around equipment to allow for safe and efficient maintenance. Regular maintenance is essential for ensuring the safe and reliable operation of an electrical system. Maintenance tasks may include inspecting and testing equipment, tightening connections, and replacing worn or damaged components. A preventive maintenance program should be established to identify and address potential problems before they lead to equipment failure or safety hazards. The National Electrical Code provides guidance on the frequency and scope of maintenance tasks. In addition to preventive maintenance, it is also important to have a plan in place for responding to electrical emergencies. Electrical emergencies may include power outages, equipment failures, or electrical fires. A qualified electrician should be available to respond to emergencies promptly and safely. Emergency procedures should be documented and communicated to all relevant personnel. Finally, it is important to document all aspects of the electrical system, including design calculations, equipment specifications, wiring diagrams, and maintenance records. This documentation can be valuable for troubleshooting problems, planning future upgrades, and ensuring compliance with codes and regulations. The documentation should be stored in a safe and accessible location. The information provided here is intended for general guidance only and should not be considered a substitute for professional engineering advice. It is essential to consult with qualified professionals when designing and installing electrical systems to ensure that they are safe, reliable, and compliant with all applicable codes and regulations.